So we really just have one more thing left in this chapter, or maybe two more things. We're going to do conservation of momentum, uh, which I think that you'll find that fairly straightforward, just in the sense that, you know, with chapter 4, like when we were dealing with the inclined plane and forces and all that, you had about a million different scenarios that you could consider. And there was a process, and you use the same process for each scenario. But with these problems, they're largely what you see is what you get. There aren't really that many scenarios that you can consider. So we'll see that with conservation of momentum. And then we'll also look at elastic collisions, where not only is momentum conserved, we'll find that momentum is conserved in all collisions, but in some collisions, you have not only momentum, but also energy conserved, like in the collisions between gas particles. And so we'll solve for that type of scenario, determining what are the final velocities of the particles. You'll definitely see one of these types of problems on your next test in the free response. And so make sure that you master it, because it'll definitely be on there, and it'll be largely like what we see in class, just with different numbers. Okay, so conservation of momentum is just, it's a law, and it says that the total momentum of particles in a system is conserved. This assumes, of course, that no external forces we had the same thing with conservation of energy, right? That no energy is going into or leaving the system, and that's true for conservation of momentum, that we have no external forces which are changing the overall momentum of the system. Because you remember, Newton's second law is F is dp dt, that if I have an external force, it changes the momentum of the system. And if that's the case, then conservation of momentum won't apply, because your momentum's changing, right, based on this force that's being applied. So anyway, the conservation momentum just says that the initial momentum, which remember is a vector quantity, is equal to the final momentum. Let's just do a simple one-dimensional problem. Now on your test, you'll likely have a two-dimensional problem, but let's do a one-dimensional problem just to start out. The two-dimensional problem isn't really that big of a step. You're just, instead of looking at the x direction only, you're looking at the x and y directions. You'll find we'll do one probably next time in 2 dimensions. But let's say that I have two particles, they collide, and then they rebound. Morning, guys. These are the masses of the particles. The initial velocity of the first one is 1 meter per second. The initial velocity of the second one is -2 meters per second. You know, one of the big things on these is getting the signs right. So when you're working through these problems, make sure that you get the signs written correctly. I always like to draw a picture. It helps me to sort of see it a lot better. And hopefully on your test, I'll probably give you a diagram, something like this, if it's just two particles that we're dealing with. Okay, so let's see, M1 is 3 kilograms, M2 is 4 kilograms. And then after the collision, I tell you the final velocity of M1 is -5 meters per second. And I want to know what is the final velocity of that second particle. All right, so I want to know the final velocity of that second particle. The way I'll work this is I'll say that pi is equal to pf, and then I just add up the momenta of the first two particles and set that equal to the momenta of the second two particles. That's m1 v1I plus m2 v2I. That's equal to m1 v1f plus m2 v2f. Remembering that these are all vector quantities, and so I'll need to consider the signs of those velocities. And then I just put in the numbers. So I have 3 kilograms times +1 meter per second, because it was in the positive x direction, plus, what was it, 4 kilograms times -2 meters per second equals 3 kilograms times -5 plus 4 kilograms times V2F. Now, You should get a pretty good feel for, is this going to be in the positive or negative direction? What do you think V2F, is it going to be positive or negative? Let's go back up to that diagram. Is the final velocity of that M2 going to be positive or negative? Right, I've drawn it positive here, but you could probably imagine that if M1, if it rebounds in the negative direction, then M2 is going to rebound in the positive direction. Uh, so there is some intuition that sort of help you with that. Though you should never rely upon intuition, of course, because sometimes your intuition is wrong, but it can help you to sort of go back and check your problem for mistakes. So I can work this. I have 3 minus 8, that's negative 5, equals negative 15, plus 4 V2F. So that's 15 minus 5, 10, divided by 4, equals V2F. What's that? 5 halves. That's 2.5 meters per second. All right. Let's do this next problem, this Men in Black problem, or not Men in Black, we'll do the dodgeball. You ever seen Dodgeball, this movie? It's about the dodgeball team. I forget, it's with Peter LaFleur, his dodgeball team. What were they called? Average Joes, yeah. So the Average Joes are going up against this other sort of evil dodgeball team. What was the name of them? The Cobras, right. And so in this final scene, you have Peter LaFleur and White Goodman facing off in this sort of death match, this dodgeball death match. And White Goodman throws a ball at Peter LaFleur's head. Or no, it's the other way around, right? Peter LaFleur throws a ball at White Goodman's head and it knocks him back. We want to consider this in terms of momentum. I want you to think about what is the system. Right, we have a system in which there are particles that are colliding. So what are those particles? And we'll estimate some of their masses and velocities, and we'll figure out. I want to know. Well, let's just watch the clip first, and then we'll sort of frame the problem. Okay, so what are the objects that are involved in the system, this collision? Right, we have the face, or his whole body, actually. His whole body moves, right? What else do we have? The ball, right? We have the dodgeball. So consider the initial state, and then we consider the final state. Initially, we have the ball moving with a certain velocity. I want to know what that velocity is. That's the velocity of the ball. We can estimate the mass of the dodgeball. What is it roughly, a dodgeball? How much? Oh, you were reading it, weren't you? Yeah, it's about a half a kilogram. That's a little heavy for a dodgeball, but it's roughly that. About a half a kilogram. And then I have White Goodman standing here. What's his initial velocity? Right, so he's initially at rest. His initial velocity is 0. And then if you watch the clip, actually, the ball, it just falls to the ground. And so its final velocity is equal to 0. And then White Goodman, he gets knocked back. How far does he get knocked back, roughly? Maybe 2 meters in about a second. So roughly, maybe 2 meters per second. You know, it's not a half a meter per second. It's not 10 meters per second. So roughly 2 meters per second. All right. So I say that this initial momentum is equal to this final momentum. Now, I have 4 different terms here, but some of the terms are going to be 0. So for example, the momentum of White Goodman here is 0, and the momentum of the ball here is 0. The momentum of the ball here is m times v, and the momentum here is m times v. So I'm only going to consider those 2 that are non-zero. That's going to be the mass of the ball times its initial velocity. I want to know what is this value times the mass of White Goodman times his final velocity. So I have those values. Mass of the ball is 0.5. VI is equal to the mass of White Goodman. What do you think? He's a pretty big guy, like he's pretty strong. How many kilograms is he? He's about 100. 70 is sort of typical, but he's bigger than most. So we'll say that he's 100 kilograms times VF, which is, what do we say, 2 meters per second. So if we calculate now the initial velocity of the ball, that's 200 over a half. That's 400 meters per second. That's a really fast speed. Like for a frame of reference, the muzzle velocity of a handgun. Do you have any idea what that is? Yeah, about 200, 300 meters per second for a handgun. So this is about twice as fast as a bullet coming out of a pistol. All right, we'll stop there. We'll pick back up with this. Listen, guys, the next test is only going to cover 2 chapters for y'all. So I really want everybody to do well because they're not easy chapters, but they're easier chapters. So everybody, I want to get 100%. It's a lot easier for me. Like if everybody does 100%, man, it takes me like 5 minutes to score a perfect paper. Okay, so I'd really appreciate that if y'all could do that. Y'all can do that for me? Yeah. All right. I won't make you spread out. But listen, guys, it's just a little assessment. Just keep your eyes on your own paper, okay? Your integrity is not worth a few points that you might pick up from looking on somebody else. In fact, if you look on somebody else, you might not pick up any points. You might lose points. So um, I'll trust you in that.